All right, we're going to have a little refresher on what we've learned about work and energy. Remembering back to the first lesson on work, we defined work as equal to force times distance, and we said a little bit more than that, it's the component of force in the direction of motion. So if motion is this way and the force is this way, it's only the horizontal component of that force that counts. So we came up with this equation, which is force times the cosine of the angle theta times the distance. And that angle theta is the angle between the direction of force and the direction of motion. We saw kinetic energy is equal to half mv squared. So as the speed increases, the amount of kinetic energy increases even faster. So if we double the speed, the energy goes up by a factor of 4. And if we increase the mass, then obviously the kinetic energy goes up as well. We saw the work energy theorem, which we defined as work done by a net force is equal to a change in kinetic energy. We know this because of Newton's second law. If there is a net force acting on an object, that object has to accelerate because F net is equal to ma. And if an object is accelerating, then its kinetic energy is changing. Okay, so work done by a net force leads to a change in kinetic energy. We said the potential energy, at least gravitational potential energy, is equal to mgh, which means the mass of the object times the gravitational field strength. So together those two things make the weight of the object times the height of which the object is sitting above the ground. Okay? This value gives you how much work gravity will do on that object to bring it down to ground level. Because how much force does gravity apply? Well, it applies the weight of the object, which is m times g. And how far will it pull it? It will pull it the height of the object is sitting above the ground. And so work is equal to force times distance, mg times h. And if you have an object sitting at some height, it has the potential for gravity to do work on it. Therefore, potential energy is equal to mgh. And we said that total mechanical energy is equal to the sum of all the other energies, and typically we'd be looking at kinetic energy and potential energy, certainly at this level. So the sum of gravitational and potential energy together leads to what's called the total mechanical energy. We can also look at other types of energy. So there may be elastic energy, there may be electrical energy, there may be magnetic field energy in there, there may be spring potential energy, there may be rotational energy. So all of that could be combined into total mechanical energy, but typically at this level we'll be looking at that combination of potential and kinetic. And we know that as one goes down, the other will go up. And so the sum of those two gives us the total mechanical energy. Okay. And we looked at work done by non-conservative forces. So these are forces that cannot store energy as potential energy. So work done by non-conservative forces means we are taking away from or adding energy to a system. And so the work done by non-conservative forces leads to a change in total mechanical energy. Okay, so let's look at this formula a little bit further. Work done by a non-conservative force leads to a change in energy, or we can say the final energy minus the initial energy. This is a very deceptively simple equation, but it's immensely powerful, and I'll show you why. This is probably one of my favorite physics equations, and yes, I'm kind of nerdy enough to have a favorite physics equation. This is probably one of my favorite physics equations because it is so powerful at solving work and energy problems. Okay, so let's look at this again. So E, in this case, is the total mechanical energy, the sum of the potential and kinetic energies. And we can rewrite the equation like this. We can say that the final energy of the system is equal to the initial energy of the system plus whatever work we do on it, or which may be adding energy to it or taking energy away from it. So whatever we wind up with is whatever we started with plus whatever we do to it. An analogy, we said that work and energy, that energy is kind of like an accounting system. So if I give you $10, you have $10, unless I give you more money or take money away. It's the same thing. The final energy here is the same as the initial energy unless we add or take away energy in the form of work by non-conservative forces. So how do we use this? If we have this formula, Wnc is equal to delta E, we can start to unpack it and we can show you how powerful it is. So, again, so the work done by non-conservative forces is equal to the final energy minus initial energy. Those are total mechanical energy values. So those in turn are made up of kinetic and potential components. So if we have our total final energy and our total initial mechanical energy, those are made up of kinetic and potential components. Now we know the formulas for kinetic energy and for potential energy, so if we drop those in, we get this great big long kind of scary looking equation, this one here. But those are equations that we're used to dealing with, and we can just plug values in. Okay, so starting from little humble beginnings, Wnc equals delta E, we get this big long equation that we can just kind of unpack, and then we can plug our values in. Now one of the cool things is that if Wnc, if the work done by non-conservative forces is equal to 0, so if all of the forces are conservative, then we have our final energy is equal to our initial energy, and we have a nice conservation of energy question. But let's look at a non-conservative force question. Okay. So, hypothetically, and not so hypothetically, I did look these numbers up. If we have a 747 jumbo jet with a mass of 320,000 kilograms, and at liftoff, so at the point where that plane is taking off the ground, its speed is 81 meters per second. It reaches a cruising speed of 250 meters per second at an altitude of 10,000 meters. Okay, so ground level, 81 meters per second, 10,000 meters, 10 kilometers up, it's traveling at 250 meters per second. So how much work is done by the engines between lifting up off the ground and reaching cruising speed? So to get you started, the thrust from the engines is a non-conservative force, so we're looking at non-conservative work. Okay? Let's see how this plays out. If we have our great long formula for non-conservative work, that one there, we can just start plugging our values in. We know we're looking for the non-conservative work done by the engines. That non-conservative work is what's going to lift it from ground level up to cruising speed. So, just plugging in the numbers, we've got 320,000 for the mass, 320,000 kilos. We have 250 meters per second for the speed, 9.8 for gravity, and so on. So we just plug those values in, and we wind up with these great long equations. And then as we simplify, we see that the final kinetic energy is 1 times 10 to the 10 joules. The final potential energy is 3.14 times 10 to the 10 joules. The initial kinetic energy is 1.04 times 10 to the 9 joules, and the initial potential energy is 0 because it's at ground level. It can't fall any lower, so it's got no initial potential energy. We take those terms, we subtract that initial kinetic energy from the final kinetic energy, and we wind up with 4.03 times 10 to the 10 joules, or 40.3 gigajoules. And that's how much energy is expended by the engines just to lift the plane up to that height and get it up to speed. That, of course, doesn't count the work done to fight air resistance and so on. That would be a much, much bigger number. But it gives you an idea of the scale and magnitude of the energies involved with that kind of thing. And it takes a complex problem and breaks it down into its individual components so that it can be solved fairly easily. I hope this was helpful in getting to understand these equations and getting a feel for solving problems with them.